Hello everyone, in this video we are going to discuss the entropy for irreversible process, and we will also discuss the entropy for irreversible cyclic process, and we will discuss the entropy for universe and the system and the surroundings. We will differentiate the change in entropy for the system, surrounding and universe. First of all, we have to consider uh, the entropy for irreversible process. As in the last video we have discussed the change in entropy for reversible process. For example, the process goes from A to B, then the change in entropy for reversible process is equal to the integral dq reversible over capital T. We can write this expression because the change in entropy is state function, then it is written as SB minus SA is equal to the integral dq reversible over capital T and our limits from A to B. And this is for the reversible process. And because this entropy only depends upon the initial and final state, whether the process is reversible or irreversible, then we can write this change in entropy for irreversible process is the integral dq over capital T, and the process goes from A to B. And this is the change in entropy as B, entropy at B minus the entropy at A is equal to the integral from A to B and dq over capital T for irreversible process. Now consider an example of this irreversible process. In last video we have discussed the example of a reversible process in which we consider a system which is in thermally contact with surrounding, and the temperature of the system is T1 and the temperature of the surrounding is T2. And let's say we have some compression in system, then due to the compression the temperature of the system may increase and the heat will produce, and this heat will flow from the system to surrounding as the temperature of T1 is greater than T2, and some D2 heat is traveling from this. And it is irreversible process, and because it is irreversible process, then temperature T1 is not equal to T2, and when the heat travels from system to surrounding, the temperature of T1 our system will decrease and the temperature of the surrounding may increase. This temperature will increase because the heat is entering in the surrounding, and the temperature of the system will decrease because the heat is leaving from the system. And at equilibrium both have temperature T equilibrium and T equilibrium. After some time the heat dq flows from the system to the surrounding, then its temperature will be at equilibrium Te. Now we have to consider the change in entropy of the system and change in entropy of the surrounding and overall the change in entropy of the universe. And if we write the change in entropy for the universe, the change in entropy for universe is equal to the change in entropy for system plus change in entropy for surrounding. The change in entropy for the universe is equal to the change in entropy of the system will be written as the integral dq over capital T, and because the heat is leaving from the system and we will consider it's negative, and the temperature will change from T1 to Te plus the integral, the change in entropy of the surrounding is dq over capital T, and its temperature will change from T2 to Te. The dq can be written as if we apply the heat to a body, it will be equal to m c and dt. C is a specific heat, m is the mass of the body, and dt. Let's consider both have the same specific heat, both have the same identical objects. That's why the specific heat of the both objects will be the same. and dq is equal to mc dt over capital T plus, and the limits from t1 to te, plus integral mc, the mass is same for the both system and surrounding, for example, and dq is equal to mc dt divided by capital T and t2 to te. If we integrate this, we will get the change in entropy for the surrounding is equal to change in entropy for the universe is equal to mc, because the mc is constant from the both terms, and we will get the natural log of capital T for the first side this, and limits from t1 to te, and it is minus and the plus, the natural log of capital T and the limits from t2 to te. Now change in entropy is equal to minus, this minus is just for this here, the natural log, the just mc. If we put the values of limits in this, we will get the natural log minus natural log of te over t1 plus the natural log of te over t2. Now the change in entropy for the universe is equal to mc natural log of te over t2 and divided by te over t1. te and te will be the cancel out, and we will get the change in entropy for the universe is equal to mc the natural log of t1 divided by t2. As we know that the t1 is greater than t2 because the temperature of the system is greater, then here the t1 and t2 comparison, t1 over t2 is greater than t1 is greater than t2. That's why the ratio of t1 over t2 will be greater than 1, and the natural log of greater than 1 will be the positive number. That's why the change in entropy of the universe is a positive number, and we can say the change in entropy for the universe for irreversible process is greater than 0. Now consider the change in entropy for irreversible cyclic process. Irreversible cyclic process. In last video we have discussed the change in entropy for our reversible cyclic process, and that was 0, and because it is a state function, it only depends upon the initial and final state, and it is irreversible cyclic process, and the change in entropy for the system is also 0 because it is a cyclic process. The change in entropy is 0 because of its state function. But irreversible cyclic process, if we consider the change in entropy of the universe and change in entropy of system and surrounding, then the picture will be different, and we will discuss the change in entropy for universe is equal to the change in entropy for the system plus change in entropy for surrounding. According to the Clausius theorem, we have discussed for irreversible cyclic process, the dq over capital T is less than 0. And if dq over capital T is less than 0 for the system, it means that the some heat flows from the system to the surrounding. For example, this is system, and from system to surrounding, some heat dq travels from system to surrounding. That's why its closed integral dq over capital T is less than 0, because if the integral dq over capital T gives us a negative number, and we know that if the dq is negative, it means that the heat flows from the system to the surrounding. That's why the some heat goes from system to the surrounding, and according to the Clausius theorem, the change in entropy for the surrounding is not zero, it will be a positive number. The change in entropy for the irreversible cyclic process is zero, but the change in entropy of the surrounding is not zero, and we will discuss here the change in entropy for the universe. We make a partition here. Change in entropy for the universe is equal to the 0 plus change in entropy for the surrounding, which is a positive number. And from here we say that the change in entropy for the universe is greater than 0. For our this discussion, we have concluded that the change in entropy of the universe may greater than 0 or just equal to 0 for the reversible cyclic process. The change in entropy of the universe is 0, but the change in entropy for the reversible process or irreversible process or irreversible cyclic process, the change in entropy is always positive number. It means that the entropy just increases in these processes, irreversible cyclic process or irreversible process. Thanks for watching.